Today we shall discuss file systems. This shall be the first class on file systems, and we shall try to introduce the basic ideas of files. We shall not go into the details of how file systems work in various operating system environments, but the basics will be introduced, and then we shall move on to the important aspects which are related to database management systems. In particular, the database management systems may or may not use the file systems provided by the operating system on a particular environment. If it does, then it will use only the operating system calls. Otherwise, it will design its own file system, or it will design a layer over the operating system to operate the file system. Particularly, we have 2 or 3 aspects in which the actual file system has to be accessed by the database. 2 important items have to be physically stored. One is the data dictionary. The data dictionary, which is defined during the DDL compilation, the data definition has to be done in the DDL, the data definition language, and the data dictionary is formed, which is stored somewhere physically. The second type of data which has to be physically stored is the actual database. The data relating to each of the relations in the relational database will have to be physically stored. The queries and etc. can be processed, and then the queries may be dropped, because these are just intermittent processes, whereas the data dictionary and the database will have to be physically stored and kept for a reasonably large amount of time. So these are the 2 things which are actually of importance regarding physical storage. So we have got to store the data dictionary and the database itself. Now we will see the other items which have to be stored are intermediate computations, queries, intermediate computation, queries, etc. So these are all which the database requires to interact and store. Now, before going into what the database does, we have to see what are the types of physical storage media which are available. For example, we have got the processor memory and secondary storage hierarchy, which is the standard hierarchy which is known to us. This is the CPU, and connected to the CPU in the logical form is the cache memory. Then we have got what is called the main store or the main memory. Which is in turn connected to the secondary memory. The cache is a very small high-speed memory which is reasonably compatible to the speed of the central processing unit. The main memory is larger than the cache, but it is slightly slower, and the secondary memory is the largest of all of them and is the slowest. The difference between these and the secondary memory and the cache and the main memory are significant, in the sense it is not the speed only by which they differ. They also differ by the volatility or the retentive capacity of the main memory, the cache, and the secondary memory. These are called volatile memories, whereas this is a non-volatile storage. These are on as long as power is on, and this is remains, the data here remains even if power is off. So this is stored in a magnetic media, whereas these are stored using the RAM technology, the random access memory technology, and the cache, as we know, is an associative memory. It is not our intention to study these in details, but which of them are important for which purpose regarding a database management system is what will be of major concern to us. So the secondary memory can be of two major types. One is the disk and the second is the tape. The disk is a direct access storage device in which you can access any location directly, whereas the tape is inherently a sequential device in which you have to start from the beginning and sequentially access portions of the storage medium to reach the particular point which is required. Now, regarding the tasks of the database, these two definitely require non-volatile memory. Whereas queries and other intermediate computation can be done in the main memory of the. This can or may be performed Therefore, our study of how to store the data dictionary and the actual database itself on a non-volatile storage will be of primary importance, because the access time, the speed and every other thing will be of value here. The computation here is similar to the amount of computation that we do on the main memory, and the analysis of these programs can be done as we analyze the main programs which are normally written on a computer in the standard algorithm design techniques of analysis. Among the two secondary storage devices, that is the tape and the disk, nowadays technology is such that the disk, we have got large amount of disk capacity. That is, we can have disks which are now are capable of storing large amount of data, and not a single disk, we can connect more than one disk to a particular machine, and in a networked environment or a distributed environment we can have several such disk storage devices. Therefore, tape storage is usually an archival mechanism which is used to store backup information, whereas actual processing is done on disk because it is a direct access device which is much faster than a normal tape storage mechanism. So the database and the data dictionary etc. are usually stored in a disk device. So we will be concerned mainly with studies on disk storage. Suppose this is the disk, then when you have the data definition language and the data definition language pre-compiler or the compiler processes the data definition and stores the items in the data dictionary. So we have the concept of something called the data dictionary, and through our insert, delete and other operations we have what we have got, the actual data or the data files. We have got some other information like indices etc. which we shall come to later on, but the user does not directly interact with the files. Every file system has got what is called a file manager. And all interactions with all the related data of files goes through the file manager. Therefore, even the DDL pre-compiler when it forms the data dictionary, it must consult the file manager to form the data dictionary. So, the data which is stored on the disk always goes through the file manager, and as we have seen before, in a database management system we have a very important entity which is called the database manager. This program or a set of programs controls the interaction of all the queries. This one is the database manager. It controls the interaction of all the queries, all the processing related to the data files through the file manager. That is, all queries, application programs which require to access the disk, the data files through the file manager, access it through the database manager. We have discussed this before in the initial introductory portions of this course, and this database manager includes not only the file handling capacities, it has got lot of other features as well, which we shall come to much later on. Our objective will now be to study the basic mechanism of a disk storage device and how files are stored on the disk, how files are organized, how tables are finally converted to files and organized, and how accessing can be made faster through various structuring mechanisms of data files. The disk, schematically, if we go through a disk, it consists of a set of disks. Instead of one disk, there are many disks like this, and we have a number of disk heads. I am drawing one, but there may be two on both sides of each of these disks. Now, these disk heads are capable of reading and writing onto this magnetic storage device, and this device spins on a spindle at a very high speed. Therefore, whenever this actuator which moves this disk, these heads simultaneously, they may move independently or simultaneously. There are various kinds of technologies, but let us assume all of them move together and they position themselves at one point of the disk, and while the disk rotates, like we had in our old records, the data is stored in what are circular concentric tracks in a magnetic format. We are not here to discuss the details of the format and the mechanism by which the 0-1 binary numbers are stored, but once the head positions itself here, then it can read all the data which is available on this track because of with the speed of rotation. It can also write on these elements. Therefore, there are two aspects of reading and writing on a disk. One is positioning the head onto the proper place, and then due to the rotation you can start reading or writing from this disk. There are a lot of details involved in these, but this is a schematic idea and that will be sufficient for our present purpose. In a disk storage, we have two types of times which are required to read or write a particular type of data. One is called the seek time. This is the time which is required to place the head on the track. And the second is latency. This is the time required to read some unit of data. Now what is this? So first is the time to position the head on the particular relevant track on which I want to read the data, and the second is while the disk rotates, I have to read that amount of information. That is, it may be proportional in the worst case to the total rotation of the disk, one cycle rotation of the disk. So these are the two times involved in actually reading or writing a particular type of information. Now we see how we organize the data on the disk. The basic unit, as we have seen, is a track. Once we position ourselves on the head, we have a track. A track may be a logical, physical track, one track, or it may be a logical track which consists of a set of tracks which is actually called a cylinder, in the sense that the head, when it positions itself on one particular track position on a spindle which has got more than one disk platters, then more than one actual tracks are available and you can simultaneously read so much of information. So this is often called a cylinder, because we have got a concentric amount of information. Now each of these tracks is organized into what are called blocks. Blocks are organized into what are called records, and records are organized into what are called files. This is how we lead to the files which we store from our tables. We conceive of tables to be converted to files, but actually these files are stored in terms of records, records are stored in terms of blocks, and blocks are stored on the tracks of a disk. And it is through this, the track number, the block number of on the track, the record number on the block, which we will be able to access the actual data that which we have. So if we just open up a track which is a concentric circle like this, if we just cut it and just unfold it and open it like this, then suppose the track looks like, and we have added some dimension to it, but actually it may not mean anything. So suppose the track will look like this. It will have a beginning of a track, it will have the end of a track. So at some point there will be a track beginning and there will be a track end. So these two are actually rolled on. If you join these two, there is little difference between this point and this point. Just this marks the track beginning and this marks the track end, and there may be a little bit of overlap, after which you can join these two. And this is one track. Suppose this is one track, and this track is identified by the track number on the disk. Then this track is organized into what are called blocks. This is a block B1. There are 3 blocks here. There are 3 blocks here. So, and between 2 blocks we have some information which is called the inter-block gap. The inter-block gap, which before a block there is a gap which is called the inter-block gap. There may be some gap here, there may be some special type of encoding or data which will ensure that this is an inter-block gap. It may also place the block number on that block. Now what is the importance of a block? The block is the unit of data that is read at one single shot through the disk. That is, when you give read, it does not read one bit of data or one byte of data. It reads slightly more than that. It reads what is called one block of data. And this is usually much more than 1 byte or 2 bytes. It may be 512 bytes, it may be 1 kilobyte, and things like that. So when you read from the main memory, for example, you read only 1 byte, which is the size of a data element of the main memory. Whereas when you read from a disk or the secondary memory, you read 1 block, which is a unit. And since you read 1 block, the concept of a block is a very important unit in deciding the organization of the data. because you are not storing it in bitwise or in bytewise information, because when you write you have to write that whole block, when you read you have to read that whole block. You cannot write or read individual portions just like that. So a track is divided into a set of blocks, and for example this may be a wastage. It depends on the integral number of blocks that you have on the track size and the block size. There may be a loss of information, there may be a loss of space or storage because of the interblock gap, and because the interblock gap is necessary, but if the unit of a block and that of a track differ, then there may be a reasonable amount of wastage. So this is some wastage which has to be accepted. Next we come to the organization of records within blocks. Records within blocks may be of various types. We may have fixed length blocking for fixed length records, we may have variable length unspanned records, and we may have variable length spanned records. Let us see them, what they mean one by one. So first we will discuss fixed length records. Fixed length records will come up in various ways. So let us first see how records come up. Records are a direct consequence of the tables. We have got a table which has been logically designed, and once we have a table, this table has got certain attributes, and each attribute has got a certain type. So this is an attribute A which is of type character string of size 20, B which is an integer, and C which may just be a single character, or it may be a boolean 1 or 0, or it may be a date. Now corresponding to such a table, we may form a file. Corresponding to each table we may form a file, and that file will contain, each tuple in that file will be in this table will be a record in this file. So each tuple in this table will be a record in this file, and the record will be organized based on these attributes. It is quite logical that the first portion of the record will be A, the second may be B, and the third may be C. And we may have fixed length records in the sense that all records will be of the size of this, and the first part will, so many bits will store the part A, so many bits will store the attribute B, and so many bits or bytes will store the attribute C. So that will be the single record information, and if we store one table per file and we fix the size of this, then we have got a file of which the records are of fixed length. Now once the records are of fixed length, then we can store them in the blocks. In general, we will have records, and we will try to have records which are smaller than the size of the, each record should be estimated to be smaller than the size of a block. If that is when we really discuss fixed length records. So if we have a track like this, and if we have a block here, the interblock gap, another block, interblock gap. So this is a block, this is another block, this is block B1, this is block B2, and these two are interblock gaps. So I am just drawing a portion, and we may store records like this. The first record may be stored here, R1, there will be an inter-record gap, R2, there may be an inter-record gap, and maybe R3, or if the size is a bit problematic, then we may have just R1 here, and so much of space may be wasted, because just the size of the record is such that it is not commensurate or not a multiple of the size of the block and the inter-record gap, then we may be wasting a lot of space. So, the choice of the size of a record, knowing the block size of the machine when you are doing a fixed length record is very important. When you choose it, when you form the file, you must know what is the block size. If you are going for a fixed length record, then what is your record size? Is it a multiple of the block? And you can easily see how much of disk space will be wasted. Wastage of disk space means a lot of things. If you had two records here, one after another, in one read you would have read 3 or 2, and your size is, if your size is slightly odd, then you will read only 1, and that the number of accesses to the disk is the most expensive item in comparison with normal algorithmic complexity of time, where our number of operations performed is the measure of the complexity. In this situation, the number of accesses to the disk is the main measure of complexity, and we will try and reduce the number of accesses to the disk as much as possible. So, when we organize fixed length records into blocks, we have to try and see that the record sizes are commensurate with the block sizes. So, these physical details are very important when you try to design a particular database system. Next, we come to what are called variable length records. Now, variable length records, where do they arise? Let us go back to our original example again, and we will see where variable length records arise. Somehow we may be interested in having one record for this, another record for this, and another record for this. In that situation, because maybe this single record is a bit too big to store in a particular block, then we will have to have what are called variable records. This is the first record, this is the second record, and this is the third record. And similar to the previous case of fixed length records, variable length records will also be organized in terms of R1, then a gap, R2, this may be smaller, R3 may be even smaller, we may be able to fit the next R1 here. But the case which we have considered here, this size is equal to the size of the 3. So, here the variability is not a very important criteria, because you have an idea of what is the total size, because each of the attributes will be placed one after another. Variable length records may come in to the picture in another way. We may have variable records because in one file we may store more than one table. If we start storing in one file more than one table, then obviously for one table we will have one type of record, for another table we will have another type of record structure, and they will come into the disk and be stored in any place one after another, and we will have various types of possibilities of their occurring on the disk, and therefore we can have them. But there are two types of variable length records, one which are stored on the disk. One is the unspanned type. The unspanned type does not allow a record to be part of one block and a part of the record in another block. If it is unspanned, it means that a part of the record cannot be in one block and another part in another. This cannot happen. The whole of the record must be in only one block. Variable length records may come into the picture because of various types of other data organizations. For example, if we had our book table, accession number, year of publication and title. And it was such that we had lot of common titles, then we would not like to repeat this title information for each and every record. We may like to store only all the titles consecutively, and we will have the record structure like this. There will be two types of records, one with the main thing which has got the first one, title, year of publication and accession number, and the rest of them will only have, which have got the same title, will only have year of publication and accession number. Or we may have one with only title and another with year of publication and accession number. So this is how we really generate variable length types of records also. The second aspect which we can have in variable length is variable length span records. In variable length span records, we allow part of record to be in one block and the rest of it to be on the next block. That is, if this is the interblock gap, we have a record R1 here, and part of R2 can be here, and the rest of R2 can overflow and come here. So this reduces the amount of space wastage, but you have to keep the information that only a part of it is here and the rest of it is there, and therefore getting the record and retrieving etc. is slightly more involved. So it depends on what type of record structure, how you are storing the records on the blocks. What is the block size? What is it a variable length span record? Is it an unspanned record, or is it a fixed record? What is the record size? What is its ratio with the block size? Amount of wastage? All these has to be looked into before actually designing the size of the physical record in which you store. Secondly, you may have to keep information for what are called pinned and unpinned records. Some records may be pointers to, see, these records are stored on the disk in a logical place, like you are stored in the memory in a logical place. For example, if you want to access a particular record, you may have to give the track number, the block number, and then the record number, and then the data position of the data in that record. That is how you actually access the final data, whereas the disk retrieves the block. From that block you access it. Now you may do it in a logical fashion also, in the sense that you may just give the offset from a particular base, so that the data can be stored not only in a particular fixed location on the disk, but it can be stored in a logically variable location like we do on the memory. Among them, some records may be required by other records as part of their information. For example, in a variable length record, you may have the book number and only the year of publication and the title of the books. Then those which are pointed to by some other main records are called pinned blocks, and you just cannot remove a block knowing that it is pointed to by somebody, or it has been used by somebody, or it is required by somebody. So you have to keep track of what are called pinned blocks and unpinned blocks. Unpinned blocks can be removed and stored somewhere, records can be removed and stored somewhere else, whereas those which are pinned, that means they are pointed to by somebody else physically. When you remove them, you have to be careful to update those which are pointing to this record itself. We will come to the details of this later on, but it is important to remember that there are several categories of pinned and unpinned records. So once we have studied records, now we come to files, which are basically a collection of records. And we have seen that there are two types of files which are available, which are there stored in the secondary storage. The first is the data dictionary. And this data dictionary, just like a data definition or a data structure definition, has to store various types of information, the relation names of a particular database, the attributes, their domains, what are the view definitions, the integrity constraints, which include the foreign key relationships, the functional dependencies, and all the other information, the access rights, who can use what type of information, and obviously what are the corresponding data files of each and every relation. This will be stored in a file organized, which is called the data dictionary. This data and information will be stored there, and this data dictionary will be accessed each and every time you logically access a particular database. You access a table. Once you access a table, the database manager will call the file manager. The file manager will consult the data dictionary, or the database manager will consult the data dictionary and then tell the file manager. It depends on the implementation. If you are using a file system which is a file system of the operating system, then the database manager will consult the data dictionary and then invoke the file manager. On the other hand, if you are using your own file system, then you may have a situation in which the file manager consults the data dictionary to access the corresponding file. And secondly, you will have what are the actual data files. And when you have the actual data files, we may store one relation in one file, we may store one relation in more than one files, and we may finally store many relations in one file. So it depends on what you store, how you store these data files. Your organization will also depend on it. We are just discussing the issues. We will come to the details subsequently. Presently, we are just discussing the issues which are related to this. Next, we come to what is called buffer management. Now, the block which has been read, you have got the disk. Any query is processed by the CPU. It wants to get that information. Where will it look for that information? Through the cache, it will actually look through the main storage or the main memory. If it does not find it in the main memory, then that information will be looked up from the disk. Now the disk will read one block and store it, so a block will come. Read or one block, read request or a write request will come. So if it reads, then it will read one block and store it into the memory. Now buffer management is a management scheme in which you keep track of what information of files are already present in the main memory. This is what is the main memory buffer. You keep track of what information of files, of these data files, is already present in the main memory. And if this information which is there in the main memory is sufficient, then you return the information from here only. Otherwise, you go to the concerned block and retrieve that block and put it somewhere in the memory. Now, since your memory is much smaller than the disk, you have to start managing your main memory, and you may have to replace and store and replace amount of information. Now, the more relevant information which is already present in the main memory makes the execution much faster. So, the organization in the disk must be arranged in such a way that relevant portions must be quickly available. For example, we know that there is a very simple relation of neighborhood, in the sense that whatever is used once, maybe the next record will be used next. Now, since we retrieve one whole block, we must try and ensure that those blocks which are those records which are going to be accessed one after another are kept in the same block. If they are kept in the same block, then they will be present in the memory. When one block is accessed, we will fruitfully utilize those elements which are there in that block. Otherwise, if it is totally disorganized, every time you will require one record, for the next record information, you will again access the disk and bring another block of which only one record is useful, and then throw away the rest, and then again you will bring another record. This concept is called the concept of locality of reference. It is very similar to the concept of virtual memory, which is defined to bring pages from the disk of a program, and it is also similar to the main storage cache page replacement policies. So, we will have to have a block replacement policy and here this buffer management is very crucial for the total time, because if it is already available in the main memory, you can access it directly, but if it is not available in the main memory, you have to bring the block from the secondary storage, and since space is limited, you may have to overwrite on some block which has already been brought. Now, once you overwrite on some block which has already been brought, then this block may have been already updated or may not have been already updated. If it is already updated, then you have to copy first, you have to copy it back. What are the modified contents? The whole block has to be copied back. If it is not modified, then it's fine. Nothing has to be done, because the secondary whatever was there, you've just brought it and you have read some information, you have not written anything here. But if you have written anything here, then you have to make sure you copy it back, and then you bring another one here. So, this concept of block replacement policy is very important, and you have to take care of the pinned and the unpinned records. You have to take care that those which are pointed to here, when you copy them back properly and in the same place, because in a particular block you may write them in one after another in a different place, you may write them in a particular place. So, the access, if it is directly pinning a block for its corresponding location, you have to write it to its absolutely proper place. So, these are the issues. There are detailed algorithms for buffer management, and each operating system has its own buffer management principles. There is a detailed buffer management system in the file system of a Unix operating system. We will not go into all those details, because we would like to concentrate more on the organization of the files and how the basic structure in which the files are organized. But when you work on a particular operating system, then you cannot deny that I will not look into the operating system while designing my database. I will not look into the file system of the operating system. You must have a good look at the file system of a particular operating system, whether you are working on a DOS environment or a Unix environment or any other environment, an IBM maybe 360 you are working on, or a DEC alpha, anything. So, finally, we come to how a file is organized. That is, now we will discuss at the logical level how records are organized in a file. We know how records are organized in the blocks and how blocks are organized in the tracks. So now we will concern ourselves with how records are organized in a file. We will study several such organization structures, and we will see which of them are useful under what circumstances. The first is called a heap or a pile. The second is a sequential file. The third is the indexed sequential file. Then we have got what are called hashed files, and we have got what are called B trees or B plus trees. In this course, we will mainly be doing B plus trees. So the next important aspect, with this background, we will go through the details of the various file organization